In this short video, we're going to learn how to solve a monopsony problem. Let's suppose that the US government is the only buyer of US military uniforms, so they act as a monopsonist in that market. Their inverse demand for uniforms is given by P equals 70 minus Q, where P is the price and Q is the number of uniforms in thousands. The inverse supply of uniforms is P equals 10 plus 2Q. Our goal is to determine the number of uniforms that the US government should purchase and the price they should pay to maximize their profit. What do we need to know in order to answer this question? It turns out that all we need is the inverse demand and inverse supply curve. How do we solve this question? First, we have to find the total and marginal expenditure curves. These are computed using the supply curve. Then we set the marginal expenditure curve equal to the marginal value curve and solve for Q. I think the difficulty in solving a monopsony question is the sort of use of different jargon. So when I say marginal value, I'm actually just talking about the inverse demand curve, which maps out sort of like the willingness to pay of the US government for each unit. And the marginal expenditure is computed from the supply curve because the supply curve tells us about how much the government would need to pay for each unit. So it looks kind of like a monopoly question because we're setting a marginal expenditure or marginal cost equal to a marginal revenue or marginal value here. It's a little bit different because we're looking at a single buyer rather than a single seller. Anyway, once we set marginal expenditure equal to marginal value and solve for Q, we're just going to use inverse supply to determine the price. The reason why we have to use inverse supply is because the monopsonist, the US government, figures out how much they want to buy to maximize their profit, and then they look to the supply curve to determine what price they need to offer in order to buy that many units. So I think the sort of key detail to solving a monopsony problem is you have to orient yourself to the problem, recognize that we're talking about the buyer and the buyer having control rather than the seller having control. Okay, I think we're ready to solve this question. Here's what we know. We have the inverse demand curve is 70 minus Q and the inverse supply curve is 10 plus 2Q. It can be really helpful as you write down what you know to sort of relabel these curves. So we can think of this demand curve as the marginal value curve. And the supply curve is going to have something to do with expenditure because it's the price you have to pay. I'm just going to write expenditure. It's not total expenditure, but I'm just reminding myself that that's got something to do with expenditure. What are we going to find in this question? We want to find the monopsonist's optimal quantity and price. Ultimately, we know we need to set marginal expenditure equal to marginal value. We have marginal value, but we don't have marginal expenditure. So that's our first step. We have to find total expenditure and then marginal expenditure. It turns out that total expenditure is going to be equal to the inverse supply curve times quantity. Notice that this total expenditure is the total amount of money spent on the good. In this case, it's US military uniforms, and it's price times quantity, right? So this is expenditure on uniforms. And we know that the price that the US government has to offer comes from the supply curve. So now we're going to fill in what we know. We have 10 plus 2Q all times Q, which turns into 10Q plus 2Q squared. So that's our total expenditure. If you're curious about what this supply curve really is, or inverse supply, I labeled it expenditure, but what it technically is it's technically average expenditure. That's what we call this. And we can take our average expenditure and multiply it by Q to find total expenditure. Once we have total expenditure, we can find marginal expenditure. Marginal expenditure is just the derivative of total expenditure with respect to Q. So in this case, that will be 10 plus 4Q. So we have our marginal value curve because it is provided in the form of an inverse demand curve. Then we used our inverse supply curve or average expenditure curve to find total expenditure and marginal expenditure. Our next step is to set marginal expenditure equal to marginal value and solve for Q. So we have 10 plus 4Q is equal to 70 minus Q. Collecting all of our Q's on the left-hand side, we have 5Q is equal to 60, or Q is equal to, not 30, 12. Now, technically in this question, Q is in thousands, so I'm going to write myself a little note that this is really 12,000. What do we do next? So we have our optimal Q. The US government is going to purchase 12,000 military uniforms. We want to find the price, so we're going to substitute Q equals 12 into the inverse supply curve to find price. So it goes into supply. That means that P is equal to 10 plus 2 times 12. 10 plus 24 is 34. So the idea here is that the government needs to offer $34 in order for suppliers to supply the 12,000 units that the government wants to purchase. So we have decided that the optimal quantity and price is $12,034, but we have one more question we're going to answer here. We are going to determine how much deadweight loss is generated by the monopsonist. To answer this question, a graph is really the most useful thing to look at. Let me describe the graph briefly. The marginal value curve, that's just the inverse demand curve. The average expenditure curve, that's just a jargony way of talking about the inverse supply curve. And the marginal expenditure curve is a curve that we solved for a few moments ago. When we solve for this optimal quantity and price, I want to just be clear about what we did. We set marginal expenditure equal to marginal value, and we identified this point right here, 12 units. Then we went down to the average expenditure curve, the inverse supply curve, to determine what price the government needed to offer, and it was $34. This deadweight loss is coming from the idea that more units would be bought and sold if this market was competitive, and those units would generate surplus. So this deadweight loss is the region sandwiched between the inverse demand curve and the inverse supply curve from 12 to some unknown value A. So to find the area of this triangle, we need to know A, which is the competitive quantity. It's where supply equals demand. But we also need to know point B so that we can figure out the base of the triangle. Point B turns out to be the marginal expenditure when 12 units are purchased. With values for A and B, we should easily be able to compute the area of this purple triangle. So we're going to start by computing A. A is just the competitive quantity, which means we're going to set the inverse supply equal to the inverse demand and solve for Q. So I have 10 plus 2Q is equal to 70 minus Q. Adding Q to both sides, I get 3Q is equal to 60, so Q is equal to 20. So A occurs at 20 units. We also need to compute point B. Point B is the marginal expenditure or marginal value, either one, when Q is equal to 12. I've chosen to do marginal value because that's the curve I kind of have staring me in the face. Remember, the marginal value curve is just the inverse demand curve. So all I do here is I plug 12 into my inverse demand curve. And I find P is equal to 70 minus 12, which is 58. So point B is at $58, and as we already found, point A was at 20, or in this case, 20,000. Now we have all the information we need to compute the area of this purple deadweight loss triangle. So what is that? It's going to be equal to 1/2, because it's a triangle. The base, I like to think of that as the base of the triangle, which is 58 minus 34, times the height of the triangle, which is this distance here, and that's going to be 20,000 minus 12,000. The thousands matter here because we're computing like a dollar amount of deadweight loss, and while Q is in thousands, the total quantity or the total reduction in quantity from the monopsony is 20,000 minus 12,000. So if we do a little bit of math, plug this into a calculator, we find out that the deadweight loss is equal to $96,000. So quite a lot of deadweight loss, and that's partially an artifact of the fact of quantity being in thousands.